Good evening everyone, welcome you all on my channel Ganit Setu. Today I will connect you with adjoint of a matrix and how to find the inverse of a matrix using adjoint. At the same time we will also see how to solve the system of a linear equation using inverse of a matrix. So today's class is going to be very important class for you all. In my previous class we have discussed about minors and cofactors, so I would like to recall the concept of this so that I can introduce you adjoint of A. Suppose A is a matrix of order 3 by 3, minus 1 0 1, 2 1 3, 4 minus 2 1. Then how to find cofactors? So we know that for each entry there is a corresponding minors and cofactors. So to find out cofactors corresponding to each entry, like C11, C12, C13, C21, C22, C23, C31, C32, C33. And what is the formula? You will multiply this by minus 1 raised to power 1 plus 1 into M11. So means corresponding minors, corresponding, right? Cofactor corresponding to 1 2 entries, minus 1 raised to power 1 plus 2 into M12. Minus 1 raised to the power 1 plus 3 into M13. Minus 1 raised to the power 2 plus 1 into M21. Minus 1 raised to the power 2 plus 2 into M22. Minus 1 raised to the power 2 plus 3 into M23. Minus 1 raised to the power 3 plus 1 into M31. Minus 1 raised to the power 3 plus 2 into M32. Minus 1 raised to the power 3 plus 3 into M33. This is how we find the cofactors. So here it's minus 1 raised to the power 1 plus 1, that is plus 1. So it's alternatively positive, negative, positive, negative, positive, negative, positive, negative, positive. Right, now to find out the minor. Right, so here it is M11 suppressing first row, first column. This is 2 by 2 determinant. It's 1 minus minus plus 6. 1 plus 6 is 7. So it's coming here 7. M12 minus 1 raised to the power 1 plus 2. It's a negative. Minus 1 into M12 suppressing first row, second column. It's a 2 minus 12. It's a minus 10. So ultimately it comes to be 10. M13 again it's positive here. Now my M13 means suppressing first row, third column. It's a minus 4, minus 4. It's a minus 8. M21, so it is a negative. 21 means suppressing second row, first column, remaining 2 by 2 determinant as it is this product minus this product. 0 minus minus 2 is plus 2. So 2 into minus 1 makes it minus 2 finally. C22 minus 1 raised to the power 4 is plus 1. M22 suppressing second row, second column. It's a minus 1, minus 4, minus 5. M23 suppressing second row, third column. It's 2 minus 0, it's 0. So 2 minus 0 means 2 only. Minus 1 to the power 3 plus 1. It's positive again. Right, see this is M23, C23 is clear. Second row, third column is suppressed. Minus 1 to the power 5 is minus 1. No? So minus 1 multiplied by M23 suppressing second row, third column. It's 2 only. Minus 1 into 2 makes it minus 2. Now minus 1 is to the power 4 makes it plus 1. M31 suppressing third row, first column. 0 minus 1 is minus 1. Minus 1 is to the power 5 is minus 1. Third row, second column, suppressing. It's minus 3, minus 2, minus 5. So minus minus plus 5. 3 3 suppress third row, third column. This product minus, what is minus? Minus 1. Minus 1 to the power 6 is 1. 1 multiplied by M33. It's a third row, third column suppress. It's minus 1. So minus 1 into 1. This is how we find all the cofactors. So C11 7. It's a 10. It's a minus 8. It's minus 2. It's a minus 5. It's a minus 2. Minus 1, 5, minus 1. So first we find out the cofactors. Now we define next concept that's called adjoint of matrix. So adjoint of matrix A is denoted by adjoint of A, and basically adjoint of A is transpose of cofactor matrix, means transpose of all that cofactor C11, C12, C13, C21, C22, C23, C31, C32, C33. So first you will find out cofactors corresponding to each entry, and then you have to replace these all corresponding cofactors and find its transpose. So here it will be transpose of first row corresponding cofactors are 7, 10, minus 8. 7, 10, minus 8. Second row cofactors are minus 2, minus 5, minus 2. Minus 2, minus 5, minus 2. Third row cofactors are minus 1, 5, minus 1. And now transpose it. Transpose means converting rows into columns, interchanging rows and columns. You get the, so when you transpose it, what you will get? Converting first row will become first column, second row becomes second column, third row becomes third column. This is how we find adjoint of a matrix. So adjoint of a matrix is basically transpose of the cofactor matrix. So first you will find out cofactors corresponding to each of these entries, replace all the entries with their corresponding cofactors, and then transpose it. Once you transpose it, you get adjoint of a matrix. So this is very important concept for you. So again I recall the concept of adjoint of a matrix. Adjoint of matrix A is basically transpose of cofactor matrix of A, right? And it's defined only for a square matrix. So when you take its adjoint as a transpose of cofactor matrix, again I illustrate one more example. Suppose matrix A is of order 2, minus 1, 3, 4, and you find out its adjoint. So we find out cofactor C11. Suppress first row, first column is 4, multiplied by C11 is plus C12. Suppress first row, second column. What it is? 3, but it will be minus 3 because 1 plus 2 is odd. C21, it's again odd, so sign will change. Suppress second row, first minus 1, minus 1 into minus 1 is plus 1. C22, suppress second row, second column, it's 2 only. So wherever the sum of this I and j is even, right, there is no change in the sign, but wherever it's odd, sign will change. The minor will get multiplied by minus. This is how find cofactors. Now we replace all this to find out adjoint of A. You need to find the transpose of corresponding cofactors. So corresponding cofactors are 4, minus 3, 1, 2. Now transpose it, convert rows into columns. First row becomes first column, second row becomes first row becomes first column, second row, first column becomes first row, second column becomes second row. It's the same as interchanging rows into columns. First row becomes first column, second row becomes second column. This is the adjoint of matrix. This is how we find out. Now we see some result regarding the adjoint of any matrix here. So here we got that for matrix A, the adjoint is 4, 1, minus 3 and 2. Now there is very interesting result regarding this adjoint of matrix. And this says that if you multiply matrix A by its adjoint or adjoint of a matrix by a matrix itself, this product is same as you multiply determinant A by identity matrix of the same order. So here let's try it now. First find out A into adjoint of A. First part, okay. So that's A into adjoint of A. So what is matrix A here? 2, minus 1, 3, 4. This is matrix A multiplied by its adjoint. 4, 1, minus 3, 2. Let's see what is the product. First row, first column, 2 4s are 8 plus 3. 2 1s are 2 minus 2, it's a 0. 3 4s are 12 minus 12, it's a 0. And now it's a 3 1s are 3 plus 4 2s are 8. So ultimately it is coming 11 0 0 11. Okay, this is the first part. Let's try second part. adjoint of matrix A multiplied by A. Adjoint A means 4, 1, minus 3, 2, multiplied by A means 2, minus 1, 3, 4. So let's multiply. First row, first column, 4 to the 8 plus 3, 11, minus 4 plus 4, 0, minus 6 plus 6, 0, 3 plus 8 is 11. Same. Now third one, let's try. What is determinant A for this matrix? 4, 1, minus 3, 2. Determinant means product of diagonal entry minus product of non-diagonal entry. So it's 8 minus minus plus 3. So 11. So now multiplying determinant A by identity matrix I of the same order. So determinant A value is 11 and I will be identity matrix of the same order 1, 0, 0, 1. So multiplying each entry by 11, it's 11, 0, 0, 11. See that all these values are same. And to verify this result, I would suggest you first find out determinant of A, right? So that you can check it. None of the entry while you are finding cofactor should be wrong, because if single entry is wrong, then entire adjoint of A will become wrong, because adjoint is determined by all its cofactor and then we transpose it. Right? So this was very important result, and this can be verified for any order of matrices up to 3 by 3. Now based on this, as we have seen that A multiplied by adjoint of A or adjoint of A multiplied by A is same as determinant A multiplied by I. Right? Now what is the definition of inverses? That two matrices are invertible if and only if EB into BA is equal to I. Right? Now if you divide this result or the equation throughout by determinant A, right, provided determinant is not equal to 0. Now here comes another two types of the matrices based on determinant value. That is, one is singular, non-singular. If determinant of A is 0, we call a matrix to be singular. So it is the definition of singular matrix. Any matrix whose determinant is 0 is called singular, and if its determinant is not equal to 0, it is called non-singular. Right? So based on determinant, there are other two types of the matrices, singular and non-singular. If determinant of any matrix is 0, it's called singular. If it is not 0, it's non-singular. So when it's non-singular, means when determinant is not equal to 0, we divide this equation throughout by determinant A, and what you result it here? A multiplied by adjoint of A divided by determinant of A. Here adjoint of A divided by determinant of A into multiplied by A is same as I, because determinant A cancelled by determinant A. Now suppose this matrix is B here. So A into B is same as B into A, and the result is what? I, identity matrix, right? So these both are inverse of each other. B is known as inverse of matrix A. And so whenever you find out the inverse of any matrix A, what formula we have got here now? That adjoint of A is divided by determinant of A. This way we have got now the formula to find out the inverse of any square matrix. So whenever you find the inverse of matrix, what you will do? You will find out adjoint of matrix, that means transpose of the cofactor matrix, and divided by determinant of A. But this inverse will exist only when determinant A is not equal to 0. That means when the matrix A is non-singular. This is the most important application of determinant, to find the inverse and adjoint. Right? Now I will illustrate one example on how to find the inverse of a matrix. So I will illustrate now the example to find the inverse of matrix. As we have seen that the formula is for finding inverse of any matrix is adjoint A divided by determinant A, provided determinant A is not equal to 0. So I will illustrate it through steps, and all these steps I will illustrate through an example. Right? Suppose A is a matrix of order 3 by 3. 3, 0, minus 1, 2, 4, minus 5, 1, 3, and minus 2. So to find the inverse, you find out adjoint, and the adjoint is cofactor matrix and then transpose of cofactor matrix. So if we have to find out cofactors corresponding to each of these entries, and there should not be any silly mistakes. So to find out cofactors, what I would suggest you that first to find out minors, and you write here C11, C12, C13, C21, C22, C23, C31, C32, C33. As the concept is clear now, it won't take much time for us. So I would suggest you to first find the minors. M11 suppress first row, first column. This product minus this product. Okay. Minus 8 minus plus 15. So 15 minus 8. 7. Now 1, 2. Suppress first row, second column. This product minus this product. Okay. Minus 4 plus 5. 5 minus 4. 1. First row, third column. Right. It's a 6 minus 4 is equal to 2. C21 suppressing second row, first column. Remaining these 4 entries, you will find determinant. This product minus this product is 0, minus this product is minus 3, so minus plus 3. 2, 2. Now suppressing second row, second column. This was right first, second row, first column. Now second row, second column. So second row, second column suppress these 4 entries are remaining. This product minus this product, minus 6 plus 1. 1 minus 6 is minus 5. C23 second row, third column. This product 9 minus 0, it's a 9. Now third row, starting from third row, right? So third row, suppress third row and first column. This product minus this product, it's 0 minus plus 4. 3, 2 suppressing third row, second column. This product minus this product, minus 15 plus 2, 2 minus 15 is minus 13. Now C33 third row, third column. This product minus this product, 12 minus 0, it's 12. Now as I told you, these are the minors. To check cofactors alternatively, you see that 1 plus 1 is even, so no change. Wherever the sum of these two is odd, there is change. So here it will change sign, no change. Here again change, here no change, here it is change, here no change, here it is change, no change. Right? This are got cofactors. Now what do you do to find out adjoint of this matrix A? You will find out the transpose of cofactor matrix. So transpose of this cofactors you will write here. Say 1 minus 1 2, minus 3 minus 5 minus 9, 4 13 12. Right? Convert rows into columns, interchanging this. First row becomes first column, second row becomes second column, third row becomes third column. You got adjoint also here. Now what I would say is how to find the determinant A. Let's try to find first determinant A. After finding this adjoint, you will find out the next step is calculating determinant A. So determinant A you can calculate along any row or column. As I told you, the row should be the one which includes maximum number of zeros or zeros. That will be easier for us. So here as the first row including 0, we will expand it along first row. You will simply multiply the first row entries with the corresponding cofactors and add them. So A11 multiplied by C11 plus A12 multiplied by C12 plus A13 multiplied by C13 gives us determinant A. So it's a 7 is a 21 plus 0 and then plus minus 1 into 2, it's a minus 2. So it's a 19. You can cross check the answer. You can expand it along second column also. Let's try it. So if you expand it along second column entries to be multiplied by second column corresponding cofactors and add them. So 0 into minus 1, it's 0. Then 4 into minus 5, minus 20. Then it's 3 multiplied by 13, 39. 39 minus 20, it's a 19. So likewise you can expand it along any row, along any column, determinant value will remain same. This is just for your satisfaction, you can check it in the rougher column. So we have got that determinant A is 19, which is not equal to 0. As determinant A is not equal to 0, it implies that A inverse exists. Now once we ensure that A inverse exists, your aim is to find A inverse now. So we know the formula is A inverse is equal to adjoint A divided by determinant A. Simple. So determinant A is 1 upon 19 multiplied by this is adjoint of A. 7 minus 3 4 minus 1 minus 5 13 2 9 2 minus 9 and 12. This is the inverse of A. So what are all the steps are there? Matrix A is given. You will write first cofactors to find out. So you write C11, C12, C13, C21, C22, C23, C31, C32, C33. First you find the corresponding minors. And then change the sign accordingly wherever the sum of I and j is given. No change where it's odd, it's changed. So there you have to change the sign. Now you got cofactors. Find in the adjoint to find the adjoint of matrix A. What you will do now in place of entries you will write the corresponding cofactors and transpose it. You got the adjoint of A. Now to find determinant of A, you can expand this matrix along any row or column by multiplying the element of that row or column with their corresponding cofactors and add them. So we suggest you to expand it along a row or column which includes maximum number of zeros, like here 1 0 is only maximum. So you can expand it along either first row or second column. So we have expanded along first row entries are 3 multiplied by 7 21 plus 0 multiplied by minus 1 0 plus minus 1 multiplied by 2 minus 2 so 19. We got determinant A. As it is not equal to 0, it shows that inverse of A exists. It's a non-singular matrix. Now as we have already seen, the formula of A inverse is adjoint A upon determinant of A. So determinant of A will you write outside here 1 upon 19 multiplied by adjoint A. This is how inverse we get. Very important concept here. So this example is, I think, will suffice the concept how to find the inverse, right? Now we'll discuss the next concept and application of inverse. Now it comes the application of inverse. So using inverse of a matrix, we can easily solve the system of linear equations in 2 or 3 variables. How we do it? For example, we will illustrate it. Say it's a system of linear equations in 3 variables, right? This is a linear equation, system of linear equations in 3 variables x, y, z. As their highest power of each variable is 1, we call it linear equations in 3 variables. How we can write it in the form of a matrix? So you see that the left hand side is determined by 2 matrices product, where the first matrix is determined by all these constant coefficients a1, b1, c1, constants of the first row, constants of the second row and third row. The second matrix is a column matrix, so the entries are 3 variables, right? And this is equal to another column matrix, so the entries are d1, d2, d3. You can check it. If you multiply this two, first row, first column, the entry will be a1x plus b1y plus c1z. Second entry will be a2x plus b2y plus c2z, a3x plus b3y plus c3z, and when the two matrices are equal, their corresponding entries are equal. So this is the result you get. So either you write this or you write this are same here. So this system of linear equations in 3 variables we have written in the form of matrix multiplication. So left hand side is the multiplication of 2 matrices. First matrix is determined by all the constant coefficients, where the first row by first equation, second row by second, third row by third, and the second one is a column matrix, so entries are 3 variables. The right hand side is another constant, right? This is how we write. Or we can also write it as ax equal to b, where a is this matrix, x is column matrix b. Our aim is to find the values of x, y, z. Rest are all constants given to us. Now to find this, we have to find the value of x. The question is how we remove a. To remove a, you know that a to be multiplied by a inverse. So multiplying equation throughout by a inverse. So we have multiplied the equation throughout by a inverse. Associative property can apply. A inverse into a x equal to a inverse b. But a inverse into a is identity matrix I x equal to A inverse B or x equal to A inverse B. This is how we solve the system of linear equation. We get the values of x means x, y, z. A inverse, to find A inverse, the formula you know already. A inverse is equal to adjoint A upon determinant of A. So what are the steps to solve the system of linear equations in 3 variables or 2 variables? First you write the system, convert it in the matrix form, then write like this as Ax, B, where A is this x and B. Now to find x, multiplying the equation throughout by inverse, we get directly you can write this. We get x equal to A inverse B, where A inverse is adjoint of A upon determinant of A. So you have to find now then adjoint of A and determinant of A both, and then substitute the value of A inverse. Once you put A inverse, you will get the value of x. This also I will illustrate through one example, but it's very important concept of or the application of A inverse. It's in the exam when it asks you solve the system, or can also ask you solve the following system of equation by matrix method. So the system I am illustrating here: 3x minus 2y plus 3z equal to 8, y plus 2x minus z equal to 1, 2z minus 3y plus 4x equal to 4. Solve the system of linear equations using matrix method. This is on linear course, matrix method, right? Now before you solve the equation or the system, you have to ensure that the system is arranged in the standard form. That means each equation is arranged in the standard form. The standard form is a1x plus b1y plus c1z equal to d1. Means first multiple should be of x, then y, then z. So first equation is already arranged in the standard form here. 3x minus 2y plus 3z equal to 8. But the second equation is not in the standard form. To arrange it in, first write the equation of x, term including x, then y, then z. Here also first write the term including x, then y, then z. So before you solve the system of equation, you have to be careful that whether all the equations are arranged in the standard form or not. Don't start solving in hurry. So otherwise every all your hard work will be vanished. So it's better to check that whether all the equations are arranged in the standard form. So first we arrange the system of equation in linear form, this in the standard form. Now we write it into matrix form. So or we can write it as 3 minus 2, 3, 2, 1 minus 1, 4 minus 3, 2. Coefficients of x, y, z in first equation, then second equation, then third equation. X, y, z equal to 8, 1, 4, or you can say it as ax equal to b. This is equation 1. So writing the system of equation in matrix form, ax equal to b. Now this equation 1 multiplying throughout, you write multiplying equation 1, right? So equation 1 multiplied throughout by a inverse, what we get? Now you will get x equal to a inverse b. This you can get now as equation 2, where a inverse is what? Where a inverse is adjoint a upon determinant a, and determinant a should not be equal to 3. So you write this much is done. Now you are asked to find only adjoint of a. That is the next part we will do now. So to find the adjoint, you write the corresponding cofactors as I told you earlier, right? So corresponding cofactors means C11, C12, C13, C21, C22, C23, C31, C32, C33. And how we do it, you know already. We first find the corresponding minors and change the sign. So 1, 1. First row, first column, it's a 2 minus 3 minus 1, right? 2 minus 3 minus 1. Then first row, second column, 4 minus plus 4, 4 plus 4, 8. See 1, 3. First row, third column, it's a minus 6 minus 4 minus 10. So say now starting second row, C to 1. Second row, first column is separates this product minus this product, minus 4 minus minus plus 9, 9 minus 4 is 5. 2 2 now second row, second column, 3 2s are 6 6 minus 12 is minus 6. 2, 3. Second row, third column. This product minus 9 plus 8. 8 minus 9 minus 1. Now third row. Third row, first column. So 2 minus 3 minus 1. 3, 2. Minus 3 minus 6 minus 9. 3, 3. Third row, third column, right? 3 plus 4. 4 minus 3. 3 and then minus 1 plus 4 plus 3 7. Check the sign now. No change, change, no change, change, no change, change, no change, change. Got cofactor. Now directly you can write adjoint. So adjoint of matrix A is the transpose of cofactor matrix. Directly you can transpose the cofactors. First two cofactors you can write here in first column, minus 1, minus 8, minus 10. Second row, cofactor you can write in second column here, minus 5, minus 6, 1. Then third row, third column, minus 1, 9 and 7. This is adjoint A. Now I told you find the determinant A. So to find determinant A, what you will do? You multiply first row any column. Suppose you are expanding it along first column. So multiply first column entries with the corresponding cofactors and add them. So 3 multiplied by minus 1, it's minus 3. Then 2 multiplied by minus 5, it's minus 10. Plus 4 multiplied by minus 1 is minus 4. So it's minus 17. Determinant A is not equal to 0 implies that A inverse exists. You can check it along any other row or column also. That you will get this minus 17. Now around substituting these values in equation number 2 here. We get A inverse x equal to A inverse B, right? X equal to A inverse B. So x means what? X, Y, Z equal to, this is A inverse. What is A inverse? Adjoint A upon determinant of A. Determinant A is 1 upon 17. Minus 1 upon minus 17, which you can write as minus 1 upon 17 multiplied by, this is adjoint A, and B means this is B here, 814. What we did? We substitute the value of A inverse. A inverse means adjoint A divided by determinant A. This is adjoint A divided by determinant A minus 17. And then we substitute this value of A inverse in equation number 2. So x equal to A inverse B. X means this column matrix equal to A inverse B. Now when you multiply these two, generally the entries, resulting entries will be divisible by 17 generally. That you have to ensure. So if you try it now, let's try. Minus 1 upon 17. Okay. First row multiplied by first column, what do you get? Minus 8, minus 5, minus 36. Total is what? Now minus 49. Something is wrong. So what we got it? Minus 49, which is not divisible by 17. So we should check and ensure is there any mistake if we have done. What mistake I did, like minus 1 I took from here, minus 5 also I took, but I took the 9 from the second row, which is wrong. So we are taking first row, first column, right? So it will be minus 1 into 8 is minus 8, minus 5 into 1 is minus 5, and then minus 1 into 4 is minus 4. So it's a minus 17, first entry, right? This is how we get. Now let's try second entry. So we take second row and the same column now. So minus 8 is 64, then minus 6 and minus 20. This is here minus 6 and plus 36. Check it again. 8 is 64, minus 6 plus 36. So 36 minus 6 is 30. 30 minus 64. Minus 34. Now third row. We are taking third row and the same column, so minus 80, then plus 1, plus 28. 29, 29 minus 80. It's a minus 51. And you see that this now 17, 34, 51 all are divisible by 17, right? So now what you will do, you will divide each of these entries by minus 17. The result comes 17 ones are 17, 2s are 17, 3s are 51. 1, 2, 3. So what we have got here ultimately, and I will write up this one. So finally we are getting here that x, y, z is equal to 1, 2, 3. That means this implies that x equal to 1, y equal to 2 and z equal to 3. This is how we solve the system of linear equations in 3 variables using matrix method. Very important method. I illustrate again the same example steps I will repeat. This is a system of linear equation is given in 3 variables and you are asked to solve it by matrix method. So we'll ensure that each of these equations are in the standard form. First we'll write the terms including x, then y, then z. Now writing this in the matrix form, Ax equal to B. Multiplying the equation throughout by A inverse, we get x equal to A inverse B. Now to find A inverse, formula is adjoint A upon determinant A, where determinant of A should not be equal to 0. Now how to find this? I illustrated. We find all the cofactors. And after finding this cofactor, we transpose the first row cofactor, first column, second row cofactor becomes second column, third row cofactor becomes third column, like that. So it is a transpose of cofactor, not a single. If single entry is wrong, the corresponding value of y or x, y, z will go wrong. So it will be very much careful while you are finding the cofactors. So after replacing cofactor by the corresponding entry, taking the transpose, we got adjoint A. Now determinant A, you can easily find. You have to multiply the cofactors of any particular row with the corresponding entries and add them or column. So it is minus 17. Now we write the formula. Ax equal to A inverse B, question second is there. So x equal to A inverse means adjoint A upon determinant A multiplied by B, and you ensure that generally it comes that the entries are the divisible by 17. So entries means the resulting are minus 17, minus 34, minus 15 divided by minus 17 becomes 1, 2, 3. Now you can check whether these values are satisfying all 3 equations to ensure that the values are correct. Like put here 3 ones are 3, 3 minus 4 minus 1, minus 1 plus 9, 9 minus 1 equal to 8. So this value should satisfy all 3 equations, right? This is how we solve this was very important video on how to find the adjoint. Adjoint means transpose of the cofactor matrix. After finding adjoint, how to find inverse. We have also verified one property of adjoint, that A multiplied by adjoint of A or adjoint of A multiplied by matrix A is same as determinant A multiplied by I, and using the same result we could find the value of A inverse, which is adjoint A upon determinant A. So A inverse exists only when determinant A is not equal to 0, and on this basis we have defined 2 types of the matrices: singular, non-singular. When determinant of A is 0, it is called singular matrix. When determinant A is not equal to 0, it is called non-singular matrix. So to solve the system of linear equation, we use this A inverse concept. So we first write the system of linear equation in the matrix form: Ax equal to B. Multiply equation throughout by A inverse, we get x A inverse B. Here we use A inverse to find the value of x, y, z. So after finding A inverse, we put the value of A inverse in the system of linear equation x equal to A inverse B, and this way how we get the values of x, y, z. So this way we have completed the portion of how to find inverse and adjoint. In my next video I will discuss and illustrate some more varieties of the questions which are based on inverse of a matrix, right? Without using formula, also how to find the inverse of a matrix. Some varieties of the questions we will do in my next video. So to continue with my next video, I would request you to ring the bell icon and subscribe it so that you can get the next video. So have a great day.